Would it be fine if we record? So is it fine for you if we record everything?
Yeah, sure. No worries.
Okay, very good. So welcome, people. We are very glad to have our speaker, Stefan Hudec from University of Queensland, and he's going to give us an introduction to Dirac operators. Please.
Yeah. Okay. Thank you very much, Thomas, for the introduction. So yeah, this is going to be just very basic introduction to Dirac operators and spin structures. Feel free to ask any questions. Especially, I apologize beforehand of my handwriting. So if you can't read something, just tell me somehow. I don't know. Hopefully, I will hear you. Okay, so let's start. So yeah, we're gonna start with posing very simple question. So assume we have a function f from Rn to R, and we have a Laplacian operator on Rn, right? It's defined as minus the sum of ddxi squares, right? I goes from 1 to n, f, right? And very natural question is, does there exist first order operator? Let's call it D. And let's say that D acts on the space of smooth functions from Rn to R to smooth functions of Rn to R. Right? So does there exist first order operator acting on the smooth functions on Rn such that it squares to Laplacian, right? It's a very natural question. It's very important to physics, but I don't want to mention physics here. Just purely from a mathematical standpoint, there's an interesting question. Is there a first order operator that squares to Laplacian? Okay, so let's start slowly. Let's start n equals 1. Right, in this case, Laplacian is just minus ddx squared. Right, what's d? D, well, d is some first order operator. Let's call it a ddx. And since the Dirac operator has constant coefficient, I think it's quite reasonable to assume that the Dirac is going to have, or the D, spoiler, Dirac, is going to have constant coefficients as well. So let's say A is some real number. Okay, well, now we do the squaring, right? This is what we require. To D squared equals Laplacian. And we find out that A squared equals minus 1. Well, I just said A must be real, so this doesn't work, obviously. So no, the answer is no. There does not exist such an operator. Well, now we can either give up, and this would be a very short seminar, or we can do something about it, right? And the natural choice here is, well, hang on, A squared equals minus 1. Well, I know stuff that squares to minus 1, right? For example, if A is I, by I mean the imaginary unit, well, then, yes, A squared is minus 1. So maybe we got it all wrong. It's not real functions, not functions that has values in real numbers. Maybe it's complex. Okay, I mean, a lot of stuff works when we start to read over complex numbers instead of real numbers. So maybe when we say it's on complex functions, it start to work. Well, okay, let's test second case, and it's equal to 2. Well, in this case, Laplacian is minus ddx squared minus ddy squared, right? And the general form for a first order operator is a ddx plus b ddy, right? So again, we pose our condition. We want d squared equals Laplacian. And now if you do d squared, it's going to be a squared ddx squared plus b squared ddy squared. Sorry. Plus, and this is an interesting part, AB plus BA, right? I don't want to assume the coefficients commute or anything. It's just, this is the straight, this is the nice way. ddx, dy. I know that the differentials commute because we are on Rn. Okay, so what are my conditions now? Well, a squared must be minus 1, b squared must be minus 1, and ab must be equal to minus ba. So I want two numbers that they square to minus 1. Okay, I have the imaginary number, I, and they must anti-commute, right? And that's a bit of a problem because complex numbers are commutative. Okay, I mean, now you can say, well, right, so maybe it's not C, maybe it's an H. It's quaternions, right? A can be I, B can be J, they anti-commute, they square to minus 1. So yeah, it's gonna be quaternions. And I mean, we can go on and on. You probably guessed that none of these three is actually the correct choice. But what is the correct choice then? So let me just erase the C here. What's the correct choice? Where should our functions take values such that we can square root the Laplacian?
Maybe just a quick question. So can you, or would it help if you don't ask your A and B to be constants, but to be functions? Could this somehow help the problem, or would it make things even more complicated?
And generally, this would make things even more complicated because we want to get constant functions in the end. So it's going to be quite hard. I haven't thought about it properly if that is possible, but I would guess no.
I mean, I can see that first guess would be to ask them to be constant, but in principle, they could also be functions, right?
Yeah, sure.
Okay.
But yeah, for the sake of argument, I'd say constant. And I mean, it's reasonable because we want to end up with constant coefficients, right? So generally, if it would be non-constant, we will get some derivatives out of it. Yeah, probably not going to be constant.
Okay.
Right. But yeah, thank you very much for the questions. I mean, I love questions. Thank you. Right. So the question is, what is the question mark? Right. So before I sort of reveal what is the question mark, let's consider general case if n is equal to n. Okay. Then our Dirac operator or potential Dirac operator is going to be some combinations of ddxi's. I'm just going to denote this ei for now. It's going to be obvious in a moment. And you can do the same sort of analysis as we did here. And you're going to end up with the following conditions, right? You're going to end up with for each I, ei squares to minus 1. That's completely the same reasoning for these two guys. And for each I not equal to j, you're going to get ei ej is equal to minus ej ei. So you need every pair of different indices to anti-commute. Right? So first, I'm going to offer you a small observation. These two conditions can be neatly summed up with one equation using the inner product. So if we assume that ei is an orthonormal basis with respect to the inner product, I can write up these equations as ei, sorry, ei ej plus ej ei is equal to minus 2 ei ej. I'm sorry, I've just some dry throat. Sorry. Right. So hopefully this is clear, right? The first condition gets replicated. If I is equal to j, we're going to get here 1, so it's going to be minus 2. And the second one gets replicated because these guys are orthogonal to each other. Okay. So, sorry, can you excuse me for a moment? I'm just gonna take another glass of water. Sorry, sorry. Just a minute. Very sorry. Hopefully it's gonna be better. All right. So what's gonna be the target space? What's gonna be the codomain? Right. So we can actually require all of these conditions to hold by considering the biggest possible algebra where these conditions hold. How are we gonna do that? Well, we can consider tensor algebra of Rn, right? That's the biggest algebra there is over Rn. And we're gonna factor out by a double-sided ideal generated by these exactly this relation, right? So we take double-sided ideal, that's the biggest thing. That is the smallest thing we can factor out that contains these conditions. And this guy is known as the Clifford algebra over Rn with the standard inner product. So hopefully that makes sense. Just a small remark here. On these Clifford algebras, you can actually define the Clifford algebra over any vector space and any Q, where Q is any symmetric to tensor over V star, right? And another remark, yeah, I'm gonna actually just omit the Q and the inner product here because they are, I'm gonna always assume the standard inner product, essentially. Right. So another interesting thing about Clifford algebras is that they are actually 8 periodic. So almost 8 periodic. So Clifford algebra over Rn is the same as Clifford algebra over Rn minus 8. But we now need to consider them as entries in the matrices 16 times 16. And this 8 periodicity has actually a deep connection to both periodicity, but I'm not gonna talk about it here.
Maybe just a quick question. So if you put Q equal 0, you get the exterior algebra, right?
Yes, exactly.
Right.
So if you take Clifford algebra with, let's say, Rn and 0, you're gonna get the full exterior power.
Okay, thanks.
No worries. And by the way, we have computed the first 2 Clifford algebras right here, right? So it's true that Clifford algebra over R are just complex numbers, and Clifford algebra over R2 are just quaternions. And if you're interested in how this would follow, so in R3, it's actually a direct sum of 2 quaternions. Right. So does that mean we are done? We can just take functions from Rn to Clifford algebras? I mean, we could. It would work. But actually something even bigger works. We can put there any V such that V is a representation of the Clifford algebra, right? Because in each representation, these relations gonna hold, and hence we're gonna get the these relations we need, and hence we could define the Dirac operator. Okay, awesome. And the representation works. Is there some natural choice for V? Some nice representation that we can use. It's very natural and gonna make our life easier, hopefully. Surprisingly, there is nice choice of V. So yeah. Turns out that if you take your Clifford algebra over Rn and you complexify, and by complexifying, I just mean taking the Clifford algebra over Rn and tensoring over R with C, with complex numbers. This guy is actually isomorphic, and now it depends on the parity of n. So let's say if n is odd, we're gonna get that this is isomorphic to space of endomorphisms over S plus endomorphisms over S minus. And if n is even, sorry, this isomorphic to the space of endomorphisms over some S tilde. Right? So the complex Clifford algebra are always the space of endomorphism, or a full space of endomorphisms, and either over some direct sum or over one irreducible guy. Okay, so what are these S plus, S minus, and S tilde? Well, for that, let me quickly introduce what is CL Rn plus. So these are just even elements of the Clifford algebra. I don't want to really dig deep into the grading. The point is the full tensor algebra has, so this guy has a Z grading, and this guy is homogeneous of order 2, right? Because these guys have order 2 and these guys order 0. So after the factoring, we can still distinguish between odd and even elements. And this is just the space of even elements on the Clifford algebra, right? And what actually holds, again, I'm not going to prove it, it's just an interesting thing, that the even elements of Clifford algebra are actually isomorphic to Clifford algebra one-dimensional lower, right? Essentially, you can keep the even elements and you can multiply the odd elements by the new element, the new vector, new direction in Rn. Right? And now for the very interesting part, there is actually this special subgroup called spin n that sits inside Clifford algebra, or the even part of Clifford algebra, which I just mentioned is isomorphic to Clifford algebra one-dimensional lower. Right? And now, so we can again gonna distinguish two cases. So one is if n is let's say odd. If n is odd, if n is odd, n minus 1 is even, and we're gonna get one representation. So there is S tilde. And since spin n is a subgroup, S tilde is a representation of spin n, because we are landing in the space of automorphisms and not just endomorphisms. And if n is even, we're gonna get S plus and S minus, which are two spin representations. Right? Again, because if n is even, n minus 1 is odd, and we are getting these guys. Right? So what are these S tilde and S plus and S minus? Well, as you may know, spin n is a double covering of SON, and these S tilde, S plus, and S minus are exactly the representations. I'm just going to write S, where S is either one of those. these are exactly the representations in the spin group that cannot be realized as representations. So they cannot be realized as a representation of SON, right? So if you remember the classification of representation of simple E groups or simple algebras, you know that there are these half representations with the highest value half or minus half, and they cannot be realized as a representation of the group SON. You actually need the universal cover. So yeah, I didn't mention that, but if n is greater than or equal than 3, spin n is universal cover of SO1. Okay, does it make sense? Hopefully it does. Okay, so amazing.
One question.
Yeah. Sure.
So you said that spin n sits inside of this Clifford algebra plus as a subgroup. So what is the group structure on the Clifford algebra? When you say it's a subgroup.
It's a space of endomorphisms, right?
Oh, as with addition as the group.
No, I mean Clifford algebras are the space of endomorphisms, so you can compose two elements. So if you consider those elements that have their inverse in the endomorphisms, you are inside automorphisms, and that's the group structure.
Oh, okay, got it. Thank you.
Or alternatively, you can think of it as the multiplication coming from the multiplication in the tensor power.
Okay, thank you.
Yeah, thank you for the question. Okay, so this all together answers our question, right? So when we now consider functions from Rn to S, where maybe just a note here, S is either S tilde or it's S plus direct sum with S minus. Then there is a Dirac operator defined as the sum of EI dot ddxi. This dot is called Clifford multiplication, by the way. And it's exactly, just as I just said, it's exactly just applying the endomorphism on the target space, right? And everything works. D squared is Laplacian. Awesome. So now in the rest, what is it, 6 minutes? If there are no further questions in the last 6 minutes, I'm going to try to do the same operation quickly on manifolds. Okay. So maybe the naive guess would be, well, we can just consider smooth functions on the manifold. Yeah, sorry, we are given, let's say, a Riemannian manifold. We can just consider smooth functions on M with values in this S, and it's gonna work, right? Well, it won't. And very naively, I don't wanna dig deeper into that because I have 5 minutes. It's gonna be because these EIs live in S and these DDXIs live in M. So when you change charts or change your frame, because this is obviously only local definition on a manifold, this guy is going to transform and this guy is not going to transform, and you're going to end up with a different operator. So at least using this definition, it is not well defined over the whole manifold. What we would like to have, we would like to have some bundle that transforms the same way as our tangent bundle, right? And we know how bundles that are that transform the same way looks. They are associated to the same frame bundle. So what we would like to have is some bundle, I'm going to call it S underline, that if I take all orthonormal frames, yeah, okay, let's assume this is orientable. Assume that first Stifel-Whitney class is 0. So I'm gonna take the frame bundle of all orthonormal frames, and I'm gonna associate it to S, right? And what representation should I put here? Well, it needs to be representation of SON on the space S. Well, fortunately, we have just discussed, we don't have those, right? S are exactly those representations that we cannot realize. Those are the spin representations. So this doesn't work either, unfortunately. We cannot do that. We would need the frame bundle to have somehow structure group spin n. And that's the extra condition we need to post on our manifold to have structure bundle, to have a frame bundle with structure group spin n. This is called a spin structure. And formally, I'm going to write it down. For some conditions, we're going to need an equivariance as well, but don't worry about that. So what we need is principal bundle, spin m, that double covers your bundle of orthonormal frames. And furthermore, there's this equivariant condition, which I don't want to go into too much. Essentially, here we have, again, the same double cover as we got right here, right? So these arrows are the same. And we wanted to preserve the right action on the principal bundle. This is just equivariancy of the lift. And this diagram altogether is called a spin structure. And interestingly enough, it doesn't exist on every manifold. We require the second Stiefel-Witting-Glass to be 0. And then there is a spin structure, which means we have a lift of our frame bundle to some other principal bundle that has structure group spin n. And now we can define our S, the spinor bundle. So our S is actually going to be defined as this spin structure. Now we can use rho. I'm not sure if I denoted it rho, but now it is denoted rho with S. And this bundle transforms the same way as our tangent bundle. So the definition is going to be global. And this d I dot ddx I is actually a global definition, and everything works nicely. Okay, I have 1 minute left. So in the 1 minute, I'm just gonna deliver my final remarks. Well, first of all, does this actually work? Is d squared Laplacian? Well, this result is known as a Weizenbeck formula, and d squared is actually nabla star nabla. By this, we mean just the adjoint operator to the Levi-Civita connection. Yeah, I guess quick note here. It turns out that when you're covering equivariantly your principal bundle, you can take connections the other way. So each connection in this bundle induces a connection in here. And here we have Levi-Civita, so we have connection on spin m as well. And that's exactly this connection. So it's associated connection to the Levi-Civita one. But there's an extra term of 0 order, R over 4, where R is the scalar curvature, which is quite interesting. Right? And if you let me go for 1 more minute.
Of course. Take your time.
Thank you. I'm gonna have 2 more remarks. One is we can actually define this globally, without going into the coordinates in the following way. You can look at sections of the spinor bundle. Then you apply your associated connection to the Levi-Civita one, which is gonna get you to the spinor bundle tensor cotangent bundle, right? Now you can use your musical isomorphism, which changes forms to vectors, and you get to sections of spinor bundle tensored with Tm. And now you can use your Clifford multiplication, and you're gonna get again the spinor bundle. right? Because Clifford multiplication takes an element, which this guy lives in Tm, because Tm, of course, embeds into the Clifford Tm, and Clifford Tm acts on a spinor bundle, right? So that's exactly the multiplication right here. And this is coordinate-free definition of Dirac operator on a manifold. And one more remark is, if you remember here, we choose some specific V. I choose V to be somehow canonical. We get it from the spin representation via some isomorphisms of the Clifford algebra and some space of endomorphisms. But you can choose another V and you can play similar game and it's gonna work. You're gonna get another Dirac operator, so-called. So if you actually do similar game with just the group SON, and you're gonna choose your representation to be the full exterior power, you can do similar thing. You're gonna take a sections for the full exterior power. You're gonna map it with a Levi-Civita connection to sections of the full exterior power Rn tensor T star M. Here you can do something of Clifford multiplication and get again back into the full exterior algebra of Rn. Sorry, I'm writing Rn everywhere, but I'm doing it on a manifold now. Sorry about that. Right, this Clifford algebra with this Clifford multiplication with tilde is actually, if I say phi is my one form, this Clifford multiplication is, let me write in here, is actually wedging phi plus, minus the interior product with phi. And this, another Dirac operator, let's call it d tilde, is gonna be exactly d plus delta, which is the Dirac operator for the Hodge Laplacian on forms. And you can actually have similar formulas to this one called Weizenbeck formulas as well, but the terms right here, the zero order terms, are gonna be different. Okay, that's pretty much everything I had prepared. Thank you very much.
Okay, thank you very much for this nice talk. Are there questions from the audience?
Thanks for the talk. I have two potentially stupid questions. So
Sure.
first of all, you said, like, for example, S is a representation of the spinor group, like you have a function from F from Rn to S. So what I know as a representation is like the homomorphism from the algebra or the group to the endomorphisms of a vector space, right? So when you say
Yes.
S is a representation, is S the vector space or is S?
Yes, S is the vector space, exactly. I mean this right here. So rho is the homomorphism into space of automorphisms, and S is the vector space.
Okay, I see. Thank you. And the second question was, just in the basic case of R to the N, I guess, could you elaborate again what is Clifford multiplication in the definition of D?
So D you mean right here?
Yeah, exactly. What is this multiplication?
Yeah, it's really the multiplication because EI is an element in Rn, right? And Rn embeds into your Clifford algebra, right? But the Clifford algebra is a space of is isomorphic to a space of endomorphisms. So it has naturally an action of S on S. Right? Because it's an element of the endomorphism algebra, so it can act on S. And that's the action. This is literally the action.
Okay, but how do I multiply that then with the derivative?
No, you don't multiply. This is like, sorry, I probably didn't make it clear. This is like two operations. So you take your functions from Rn to S, then you make it GDX F, and then this is again a function from Rn to S, and then you apply the Clifford multiplication.
Right. Okay. Thank you. Thank you.
So maybe like this. Yeah. Thank you for the question.
Yeah, maybe another quick question. So you said that so it's not always clear that you can find a spin structure on a manifold. So
Yes.
you have to ask this W2 to vanish. But in case you have spin structures, can you somehow measure how many you have? So is there...
Yeah. I'm not sure from top of my head, but I believe the space of the first cohomology in the value when you take values in Z2 measures the non-uniqueness of your spin structure. So actually how big this guy is, that's how many spin structures you have. Okay, it follows from long exact sequence in cohomology. Actually, I can show you the proof, but yeah.
Okay, thank you. Yeah. So are there more questions? Maybe from...
So your motivating question, whether there is some operator D that squares to the Laplacian.
Yes.
Why is this a question that you ask? Now that you know that there is such a D, what are the consequences?
I mean, for me personally, it's just an interesting mathematical question. Like, which operators can you square root and which you can't? I think that's an interesting question. I believe it has some consequences in physics, because if you manage to get the same solutions but with operator of degree 1, you have somehow more symmetry and it's more well defined. But I don't really understand that. So for me, it's just a motivating question, like purely from mathematical perspective. Can you do that? Really?
Okay, thanks.
No worries. Okay. Any more questions?
Explaining the story, and then once he did this, he was able to unify this, and he produced these equations that it was a better approach than an earlier approach, which was called some Klein-Gordon. Exactly. Yeah. This was so. With this insight, he was able to improve on the previous one, Klein-Gordon, and what came out of it was he got two solutions for matter, one which was positive and one which was negative. He thought the negative one was a mistake, but that afterwards was like the first sign of antimatter. So it's a natural question on its own, but the actual motivation for Dirac was unifying quantum mechanics and special relativity. Antimatter comes as a concept.
Thank you.
Okay. Are there some questions from people on Zoom? If yes, just unmute yourself and ask the question. If not, let's thank Stefan again. And now there's a short break, and then there will be the main talk.